and I am a paleoceanographer, so I study how the oceans circulated and their structure, both sort of tectonically and chemically, has changed in the past. And a lot of my research focuses on trying to understand how the ocean temperatures impact our large ice sheets, particularly in the southern hemisphere in the Antarctic. And so today I'm going to talk to you about a recent International Ocean Discovery Program, IODP Expedition, that we took to the Ross Sea in Antarctica in earlier this year, January to March. And I was a scientist on the ship, as well as Imogen Brown, who is a PhD student here. Imogen, raise your hand for the new folks. We study Antarctica because we want to understand more about how the system has changed and evolved in the past to understand how it might respond to warming in our ongoing climate scenario, which is getting worse by the day. So in the last 60 years in the Antarctic, we've observed atmospheric warming, mostly focused over the West Antarctic, but some suggestion that all of Antarctica, east and west, are warming. The oceans around Antarctica, the Southern Ocean in particular, is warming, and it's warming at a number of different depths, both intermediate depths and also deep, greater than 4,000 meters. And this is pretty significant because these changes in temperature can influence ultimately how the ocean circulates. We've also been losing a lot of ice mass through time, and this is an ice mass loss from 2002 to 2016 from the GRACE satellite that Dawn works on. And this data is showing where the hot spots for ice mass loss in the Antarctic are through this time. Centered here around Pine Island, here on the Antarctic Peninsula, and here in the Totten Glacier region. These orange boxes are where my lab currently has projects. So we've covered both hot spots and not so hot spots at present. So why do we care about the sort of health and stability of the Antarctic ice sheet? Well, we care because melting ice sheets contribute to sea level rise. And so we hear a lot about Greenland's ice sheet melting, and Greenland's ice sheet contains about 7 meters of sea level equivalent ice. In the Antarctic, the ice sheets are the West Antarctic ice sheet here and the East Antarctic ice sheet here. The West Antarctic ice sheet contributes about 3 to 5 meters of sea level equivalent ice, and the East Antarctic contains about 53 meters of ice. And if you guys read Discover magazine this week, we have a piece that's basically suggesting that the East Antarctic might be more unstable than previously thought, and we published this in Nature late last year. So a lot of what we're trying to do as scientists, as oceanographers, as modelers and observationalists, is try to understand how Antarctica's ice sheets will respond in the various climate scenarios of the IPCC, from RCP 2.6 through to RCP 8.5. This refers to the amount of carbon dioxide in the air, or in our Trumplandia world here. And models of the Antarctic ice sheet show that all major ice shelves in the Antarctic, the Ross, the Weddell, and the Amory, shrink in about 100 years in the models. And we can see rapid warming that also produces a lot of ice mass loss. And so a lot of these models are predicting by 2100 that you're going to have 0.1 to 0.4 meters of sea level rise. And many people suggest that that might actually be much higher. So a lot of these models are driven by paleoclimate data. So data contained in the sediments that enables us to check the models and to try to see how they respond. And we'll talk about that a little bit later. Why do we care about sea level rise? Well, I like to give this slide both in Florida and outside of Florida. So we should care a lot. Here's a map of St. Pete. Here's the College of Marine Science. Here is the future sea level rise. My house is here. I've bought in a no flood zone that will turn into a flood zone shortly. The dean's house right here is in the flood zone. So even though she's a geologist, anyways, what you will notice is here's a list of the top 30 cities with the most people affected on land from sea level rise. St. Petersburg is number 14, okay? And 19 of these cities are in Florida. And people should care, but they don't. So we can visit Mar-a-Lago when it's underwater. And so what I try to do and what my lab tries to do is to use the marine sedimentary records. So the mud at the bottom of the ocean floor collects over time. And what we can do is we can look at these layers in the mud and we can analyze them geochemically to understand how climate has changed over the past 65 million years. And we do this by drilling into these muds and also coring into these muds. And we get beautiful records like this. They don't all look like this. These are just the prettiest ones. And what we can do is then analyze these records and try to understand how climate has changed. So a really important anniversary this year, there are two. One that David talked about is sort of the plate tectonic theory. The original paper was published 50 years ago this year, and also, and not coincidentally, the ocean drilling program is 50 years old today, and we'll talk about that in a second. So marine sediments have been sampled for a long time. I always like to give a history of oceanographic sampling. So we collected the first sediments in 1873 through dredging. The first big description campaign happened starting in 1891 with the HMS Challenger, shown here. And you can actually go and look at these samples in a warehouse in South London, should you ever feel the need. They're part of the Natural History Museum's collection. And then we had our first deep sea coring expedition on the German ship, the Meteor, from 1925 to 27. And in 1968, during this time where continental drift was turning into plate tectonics, the deep sea drilling program, the first version of scientific ocean drilling, was able to confirm seafloor spreading. And since 1968, we've had various versions of this program, mostly supported by the US. It's one of the largest, one of the three largest infrastructure components of OCE at NSF, that's the Ocean Sciences. We're also great because we bring money into OCE, so you guys are able to get more funding. And we do this by renting out the ship. And so this program has run since 1968 in various different versions. So this is a question that every student of geological oceanography asks and shouldn't ask. However, but hopefully I can convince you otherwise.
Volcano has been discovered, and I know you're thinking, how could the largest volcano on Earth stay hidden? This might be hard to hear, but apparently we know next to nothing about our own planet.
Earth witness enough, the history of life, and the evolution of our planet. We need to study the vast, largely unexplored area beneath the ocean floor. Here, rocks and sediment deposits act as a logbook for Earth's history, recording both gradual changes and sudden events over the past several million years. Scientists have expanded the frontiers of human knowledge by drilling core samples from each of the world's ocean basins. Their work is far from done. The new International Ocean Discovery Program, or IODP, is carrying this work forward with a focus on 4 critical research themes. There is no better place to study Earth's climate history than the ocean floor, where climate records reach back 10 times as far as the oldest ice cores. By understanding the past, we can more accurately predict the future and assess how the planet will respond to increased carbon emissions, warmer air and water, and more acidic oceans. Scientific drilling can not only help us survey life on, but also in the seafloor. By studying the communities of bacteria and other microbes surviving in this harsh environment, we can better understand how life might have begun. We can learn to recognize the kinds of life we might find on other planets. Deep beneath the Earth's crust, the molten mantle has undergone dynamic changes over millions of years and is still evolving even today. A better understanding of these processes can teach us about the nature of plate tectonics, seafloor spreading, and continental uplift. The Earth can also move suddenly, often with disastrous results for human societies. Earthquakes, landslides, tsunamis. What causes these geohazards? With further study, we may yet be able to discern patterns and read the signals in advance. Extra warning could mean the difference between life and death. The ocean floor is a rich source of information for the worldwide scientific community, but accessing it is not easy. IODP relies on specialized vessels and equipment to recover samples from the deep. There's the JOIDUS Resolution, the US-based workhorse of the program. This flexible, adaptable vessel has been drilling samples and providing data for nearly 30 years. A thorough refit has set her up for decades of future service.
Yeah. Or not.
The Chikyu, operated by Japan, is a deep-water drillship purpose-built for scientific drilling. Her advanced capabilities offer the best chance for one day reaching the planet's mantle. And a consortium of European countries provides mission-specific platforms that can access areas off-limits to the other 2 vessels. For example, icebound seas or shallow waters. The latest innovation at IODP is the use of sub-seafloor observatories that can monitor crucial processes such as changes in temperature, pressure, and fluid flow over various timescales. Many are capable of connecting to regional networks to serve data in real time. IODP generates vast amounts of new samples, data, and experimental results. A network of facilities helps preserve this knowledge for future generations, making it openly accessible to the global scientific community. Repositories in the US, Japan, and Germany store and curate cores and send samples all over the world upon request. Websites, newsletters, and social media portals keep the public informed of the latest scientific discoveries, while specialized education programs train science teachers and instill passion for discovery in young minds across the globe. Like the ocean itself, the seafloor covers nearly 3/4 of our planet. And today, more than ever, we need to discover all it has to tell us about our past and use these lessons to inform our future.
So I figured I would show you some videos because I can't say all that in that amount of time. Many of us here have been involved in the ocean drilling program. We even have a curator from one of those facilities here right now. Katie, do you want to raise your hand? She was one of our grad students. Some of you, many of you may know her. She now works with all of those cores and sends samples all over the world to many, many scientists. So the IODP has a science plan that we are implementing from 2013 to 2023. And what I'm going to be talking about today is one of these themes of climate and ocean change that you've just learned about. And within this theme, there are two challenges that are related to Antarctica and the response of the ice sheet through time. One is, how does the Earth's climate system respond to elevated levels of atmospheric CO2? And the second challenge is, how do ice sheets and sea level respond in a warming climate? One of the things that we've been trying to do is develop transects from coastal drilling out to deep sea drilling. And so the expedition I'm going to talk about today drills some shelf and some deeper sites in this transect. So a lot of what we know about Earth's climate system and how it's evolved through time comes from the ocean drilling program and its predecessors, and from the the chemistry of these tiny fossils preserved in the sediments called foraminifera, and Pam will talk a lot about those this afternoon. And so we analyze the foraminifera for metals, for our oxygen and carbon isotopes, to try to understand how Earth's system has changed through time. And those of you who've taken a geological oceanography, this should look familiar. Those of you who haven't, don't worry, you'll learn all about this. But this is basically 65 million years of climate change from the oxygen isotopes of these foraminifera. This is my PhD advisor, Jim Kennett, and one of his closest friends, Nick Shackleton, and they generated the first record from these, well, one of the first of these benthic foraminifera in the deep sea to try to understand how Antarctica's ice sheets had changed through time. Here's a telegram that was sent basically saying that they wanted to collaborate on sediments that they had collected in the deep sea drilling program, and how about 100 samples? That would work. So what we can see is over the last 65 million years, Earth's climate has generally cooled about 12 degrees. And there are these rapid steps of change at certain periods of time that are suggested as periods of time where the ice sheets, particularly the Antarctic ice sheet, grew very rapidly. We also can see some warm events like this one here called the Miocene Climatic Optimum, which I'll talk about in a little bit. But all of these records come from very far away from the Antarctic ice sheets. And what we need to try to understand more about how the ice fluctuates through time is records from the continental shelf that show, they're not complete, but they show an advance and retreat of Antarctica's ice sheets through time. And these are some of the major campaigns that have already happened, and we're going to have two more happening in the next 2 years, one to the Amundsen Sea, which Teresa King is going on. Teresa, if you're here, raise your hand. And one to the Weddell Sea, which Michelle Coutard is going on. Raise your hand, Michelle, if you're here. And they will be sailing as physical properties specialists. So we can learn a lot about how the ice sheets respond just by looking at the sediments preserved on the seafloor. And so this is a record from the Andrill project, which was drilled from the ice very close to land. Imogen's dad was actually a sedimentologist involved in this project. And what they did was they looked at the marine sediments and to try to understand how the ice had advanced and retreated through time. This is a record of diatom oozes that suggests a period of open water with no or minimal ice. And so in a model, that's what this scenario would look like, open water. This is a record with a lot of mud and some ice rafted debris, some pebbles that have dropped out of icebergs and off the bottom of ice shelves. And that's this kind of environment, so ice proximal or, sub-ice. And then there are these dimix, which are a mix of everything that the glacier picks up and drags along and deposits. And in this scenario, the ice is covering this region, and that's what it looks like in the model. And so a lot of what we've done is tried to train the model using these marine sediment records that we've collected from areas like this is the inner Ross Sea shelf. And so in 2012, we wrote a proposal here at CMS to go back to the Ross Sea. We hadn't been there since 1973 in leg 28, and to try to understand how the ice sheet had changed through time, the West Antarctic Ice Sheet. And so we had 5 objectives, really to try to understand how temperatures, both atmospheric and oceanic, contribute to changes in ice sheet extent, and also this polar amplification. So why do temperatures seem to get much, much warmer or much, much cooler at the poles? We also really want to understand how the ocean forces both sea level and temperature, how that forces these ice sheets to be stable or unstable. And how the contribution, particularly of West Antarctica, what is that contribution through time to global sea level? A couple of other things, look at how this ice sheet is sensitive to changes in Earth's orbit, which if you guys haven't taken geological oceanography, you'll learn about as Earth's orbit changes through time. And also to try to understand how the shape of the seafloor influences the ice sheet. So here is a preview of 374, hopefully. Hello? It worked earlier.
Years ago, leg 28 of the ocean drilling program recovered cores from the Ross Sea that changed the way we think about Antarctic ice. Every decade, our knowledge has advanced through more Antarctic drilling expeditions. Now, the International Ocean Discovery Program makes a long-awaited return to the Ross Sea on Expedition 374. Scientists from 13 different nations will look back in time to understand the Antarctica of the future.
So we're going into the Ross Sea to collect cores that will recover a history of the climate and the